doing the 8 foot by 8 foot drone. Our team members are Blaze Williams, Tyler Brown, and George Bygritter. Our advisor is Dr. Alfred Gates. Next slide, please. So the problem we aim to solve is to provide a practical, cost-effective, and efficient solution to general maintenance and advertisement. Our main goal is for use in agriculture. Uh, this this drone is used to design. This is used. Can you bring back the slides, please? I can't see the slides anymore.
It should be showing the presentation. If it's sharing my application.
Yeah, I'm not seeing anything on.
You should share your screen, not your application.
Just start the slide over. The problem solving how to practice effective and goal is for agriculture this frame for with spread fertilizer. Right now, farmers with large fields using pesticides on large fields. Although we are focused on small fields right now, in the future we aim to planes and other gas consumption devices. The same is true for advertisements. As far as flying flags with buy one get one free on the beaches. We can use this drone to do that very efficiently. Next slide.
Yeah, so for the large drone, there's a number of constraints that we had to adhere to. One of the design constraints was to make it as large as we can with the motors that we have. So Dr. Gates wanted us to go with an 8 foot by 8 foot drone, and the frame is going to be intended for multiple uses and for multiple upgrades. Furthermore, we're going to keep the same frame that the group before us used. It's an H frame with some slight modifications. And Dr. Gates told us to use the thinnest material possible with included weight reduction holes to make it as lightweight as possible, but still structurally sound. Another constraint were mainly applied to motor location. The blades tips have to at least be 2 inches apart, while the motors remain 1 foot away from the main body. The aircraft is also going to be deployable and should fit inside of the back of a pickup. And we're trying to limit the amount of time it's going to take to open up. So we want this thing to open up as quickly as possible. So we're trying to do it within 20 minutes. And for target users, we have a wide range of users. Our main users are farmers and agricultural users, spread pesticides and fertilizer in a much more cost-effective, efficient way than currently being done with helicopters. In addition to that, farmers could could go out and buy this aircraft and use for their own personal use, whether it be spraying pesticide or tending to other crops. Business could use this for advertisement, like car dealerships saying, "Come here, we have the best prices," etc. This could extend to sports stadiums and them using to fly the drone over instead of the planes, or hovering in place, advertising merchandise and so forth. These drones could also be used for, like, a example, halftime shows for like football games, or flying over beaches holding other advertisements. And also, it's not limited to just advertising and agriculture. We could also expand upon bringing supplies at construction sites and other sorts of job sites. this aircraft has a lot of parts that come off previous iteration. Um, the the concept was with Dr. Gates, and that's what the previous group proved. So with this concept, we're moving forward with the same H design as the previous group used. We're also using same amount of motors, same exact motors as the other aircraft used. The main differences, though, between these two aircraft is ours is going to be deployable, while theirs was a fixed frame that couldn't fold up. And having ability to be deployable will allow us to have this drone be as big as it is, um, which is roughly 3.5 to 4 times greater in size. So this larger UAV will also be able to carry out better tasks with better stability, carrying with a large load like a flag or pesticides, with water oscillating inside of them. And another thing that this drone really relates back to the first model was that it's going to keep the autopiloting feature of programmable flight path.
Existence of drone frames for the purposes of carrying heavy loads. Many large aerospace companies already have experimental designs that work as far as their ability to carry large loads. Uh, for instance, the Boeing eVTOL CAV, it's an electric vertical takeoff and landing cargo aerial vehicle, is shown to have a load capacity of approximately 500 pounds. This drone pictured weighs approximately 700 pounds and is 15 by 18 feet by length and width and stands about 4 feet tall. Some of the challenges that Boeing has had with their own designs, both of these pictured here, include prolonged flight. They have mostly been relying on designing their own batteries to be used in their designs because they've already proven that rigid frames can fly and carry large loads for a period of time that is actually usable in industry. One of the other companies that I was able to find that produces and fabricates drones is a company called Griff Aviation. They fabricate and supply drones to companies who are looking to commission their work and adapts several of their own designs for practical uses. Their website shows their entire fleet of drones, and many of the specifications include length and width and height, like packaging, as far as how much volume this drone takes up when it's fully deployed, as well as lift capacities ranging from 600 pounds to upwards of 440 pounds. Some of the applications listed by the company for the use of their drones includes firefighting, emergency life-saving equipment deployment. Smaller drones are used in the film and television industry. Much like we hope to use for our drone, their drones are also used for the purposes of monitoring livestock as well as crops through the use of pesticides, as well as seeing what parts of the fields may need more tending, as well as construction applications, and security and law enforcement applications, more for the monitoring of activity in certain areas. As far as folding drone designs, I was not able to find any any drones being sold that are looking to achieve the load capacity we have And although they do fold, they simply don't fold on the scale we're looking to achieve with our drone.
So our team members, we naturally all have strengths and weaknesses. My strengths come from years of CNC programming as well as machine design and fluid mechanics. However, my weaknesses are heat transfer, MATLAB, and modeling of dynamic systems.
My name is Tyler Brown, and some of my strengths that I listed include CNC programming as well as machining. I have also done a lot of work with designing test procedures for a lot of the products that we make at work, and hope that knowledge can translate over to the testing of different frame designs, as well as an extensive background in solid modeling using Autodesk Inventor. And some of my weaknesses include uh, my knowledge of machine design, um, FE, finite element analysis, only because I'm taking that class now, and fluid mechanics.
My name is George Wagner. My strengths include modeling, and that comes from a large background of drawing and photography and working with my hands. Spent some time working as a volunteer on some aircraft, to give me a good knowledge of how parts are made, how what machinery could. Um, all the things I do, time management comes into a larger effect to that. So I try to spend my time wisely and most efficiently. Um, and So my weaknesses include thermodynamics, calculus theory, and finite element, only because I'm taking it right now.
Naturally, what comes to affect it with this project is the amount of designing that we have to do in order to accomplish the final project, final product. Um, Most of this project is designing. So more than 50% of our tasks come from designing using 3D software. In our case, we've been using Inventor as a 3D software to help us model and assemble all the final products that we have. This has given us a very large window for basically saying what we can accept and what we can't accept before we go through and actually create this, before we buy product and start manufacturing, which is very nice and efficient. Um, as you can see, we have many tasks that are just built around designing these components that we've become to call them in Inventor. Um, even got up to the point where we are designing stuff using motorized dimensions. That means that we can we're using a Microsoft Excel sheet to go in and edit critical dimensions like wall thickness or total length or location of holes, and we're using the Excel sheet to store this data, and we can easily change it with any kind of update to our model that we need. So this has saved us a lot of time, and I'm sure it will save us more time in the future. Um, but as far as the design tasks go, we've got, I think it was somewhere around 65% is design tasks. The rest are analysis, manufacturing, whatever the case. So what we've showed here is just the design tasks. Next slide. So these are all the other tasks that we have for our project that we felt is necessary to show you. Um, so generally, tasks associated with the design and analysis will be run parallel with each other. This ensures that we're running iterative tests to ensure that we have the right product and we can finalize component. This being said, we really don't have a lot of sequential tasks, but I mean it's obvious that before we get to the manufacturing phase, we have to buy the material first. Other than that, we have a lot of tasks that will be like intermittent tasks that will be run in a process that just goes back and forth before we get a final product.
As far as the completed tasks, so far we have identified the final design from previous iterations that would work. For instance, our group has come up with multiple designs for a single frame. This includes what we have called the Chinook design, which was considered to be too heavy once it was all assembled. We have also modeled 4 different designs and chose the H frame as our final design. Only because we found that this design was easiest to implement our weight reduction features into the model, as well as the purchasing of stock and manufacturability of the frame. We have identifying and modeling all of the individual components of the drone and using our Excel spreadsheet and performing parametric studies. We are going to be able to come up with finished dimensions for all these individual parts. Because we have finished doing this modeling correctly, we can change parameters and update our assemblies so that there won't be any issues with the model, and we can immediately go into analysis of the structure. And finally, one thing we were able to accomplish was evaluating the performance characteristics of the motors that we plan on using, as well as determining physical properties of the motors, the ESC module, propellers, as well as the motor thrust. And we also have an idea of how much this structure might possibly weigh, allowing us to determine what the load capacity will actually be.
So for the steps we have left, there's still a lot of work that remains to be done, and we plan on doing a lot over the summer, not more than ever with this outbreak. So we plan to address as much as we can now, so we don't have to play catch up later and try to leave a lot of room for troubleshooting for inevitable problems. The completion of the CAD model of the full assembly is the next step that's coming up in terms of being finished. And from this, we'll be able to perform a lot of our other tasks. So from here, we'll be able to run FEA analysis on the structures, as well as do a hand calculations to compare them to make sure everything's working out right. And then after that, we're going to be if the assembly passes the stress analysis, which will allow us to ascertain if we have to where we could put these weight reduction features, and then conduct these stress analysis intermittently while we're assessing the best places or all of these weight in allowing for the frame to be as strong as possible. Following that, the final design will be evaluated and make sure everything was within specifications of what Dr. Gates wants and what our design constraints are, and any issues are going to again be addressed and corrected. So we'll be going over with Dr. Gates our final design right before we begin building everything to make sure everything is how he wants it. And the presentation for then the senior one is being created now as we're going along, which includes a small scale prototype that represents our finished assembly when it's fully deployed.
To conclude our presentation, as well as talking about the progress of our project, we feel our group has been able to make very good progress so far on our senior project. Due to events over the last week, we are unable to meet in person as frequently as we were. Despite this, we are adapting and continuing to make sure that each member is doing what they can with the resources they have available to them, addressing problems approached while completing tasks immediately, and remaining in contact with our advisor. Doing this consistently will ensure that we will complete the tasks we set out to do this semester.